Hi, I'm Vicky Wood, your subject advisor for Maths and Statistics here at Pearson, and in today's short video we're going to be looking at problem solving in A-level maths. We're going to take a quick look at some key features of problem solving questions at A-level and what the challenges are for students before diving into some teaching strategies and resources. Let's take a look at the key features now. So in today's session, we're just going to focus largely on the pure papers and the problem solving element across all of the components are largely focused around these assessment objectives AO2, which is about mathematical communication, and AO3, which is all about the problem solving via mathematical modelling. So you've got your classic kind of show that and prove questions within the AO2 requirement, and we've also then got in an AO3 that problem solving with mathematical models, and this is where we are going to take a big focus today. Students are really quite used to and successful with modelling with, for example, exponential functions because it's something that they're really familiar with. But where we are seeing from the performance data students really struggling is to model in context from other content areas. So, for example, modelling periodic context using trigonometric functions, being given or asked to use or deduce a model using their knowledge of other functions such as modulus function or quadratic functions. And quite often these are really big wordy questions that are full of context and information, and students are really struggling to know where to get started with these. In this short video, we're going to focus largely on the pure math side of things. We do have some specific deep dives and training videos available for statistics and for some of the trickier questions in mechanics, such as ladder problems, which I'd definitely refer you to for those. So one of the key things that's really important for students to be able to access those AO2 questions and proofs in particular effectively is that they need to be very confident with that vocabulary and notation. Obviously, there's quite a lot of complex notation that students need to know, set notation, and just really understanding the language of how to construct proofs and mathematical arguments. So we really recommend embedding that vocabulary and notation right from the start of the course. A really effective and practical way of doing this is to provide each student with a bound copy of their formulae booklet, the appendix of formulae that they need to learn, and the appendix of notation that you can find from the specification. Students have that on their desk every single lesson. You can constantly be referring to it. And also, as a teacher, thinking about what annotations do you want students to be adding to their formula sheet. So, for example, deriving the double angle formulae from the compound angle formulae, all of those little add-ons, planning that in advance and making sure that you are kind of really explicitly teaching that so that students can confidently sit down and spend the first minute or so of their exam annotating their formula booklet to set them up for success. So I'm not going to spend too much time looking at proof today, just simply because we do have some dedicated deep dive sessions on proof that look into all of the different types of proof questions in a lot more detail than I could cover today. So I'd refer you to those. You can see the links there. They're on the Maths Emporium, and on screen are just some of the key points from our latest training session, some top tips there really for students and to consider in your teaching. So moving on from proof, the other area that we've identified where students are really struggling to apply those problem solving skills are in questions that have got an element of problem solving with mathematical models. So developing a deep understanding of mathematical models is really a key area of focus. So some tips here, students really need to be looking at modelling questions across all of the topics. So not just looking at exponential models, for example, but making sure that they are encountering modelling questions when they're looking at quadratic functions, when they're looking at trigonometric models. So getting that exposure is really key. So there are modelling exercises in the textbook, and we have got some resources on the Maths Emporium, and I'll show you some links to those at the end of this video. Students need to be able to define a mathematical model, what it can do and what the limitations are. These are part of the assessment objectives, and these are things that they can be explicitly assessed on. So use of visual representations obviously is really effective in helping students to develop that deeper understanding. So obviously that graphing software can be really effective. And also students really need to be able to develop that skill set of how are they going to create their own visual representation in an exam when they don't have access to, for example, Desmos. whether that is via a graphical calculator, so developing their skills in that aspect, whether it's their sketching skills, their kind of mental visualization of the function, or just simply using the table function to get some values to get a bit of insight as to, well, what is actually happening with this function? How is it behaving? And that is the real key here. How does the function behave? That is the mindset that students really need to be getting into to develop that deeper understanding and to be able to then apply that successfully in the types of questions that we see. So it's really about investing some significant time in making connections between the model, the graph, the graphical representation of what that looks like, and also then the context. So the function, the equation form, the graph, and then the contextual interpretation. So we need to kind of be over asking around these, asking students to come up with their own statements, really getting them to think about what, for example, what scenario could this equation be modelling? Given a scenario, what might the equation look like that could model that? So again, kind of things like fill in the gap exercise can be useful here, and we're going to also look at some practical tips about how we might do that for trigonometric models, because this is something from the performance data that is coming up as a definite weakness, and we are seeing these questions really quite regularly on the exams, and there's something that students are performing quite poorly on time and time again. So this topic does need some more time, and we just need to be aware of teaching some of the skills in isolation. So things like converting from the form of a cos plus b sine into the r cos or r sine forms. Actually, let's put that in context. Let's apply it in models. Why is that useful? So we're going to look at that in a bit more detail now. And on screen, you can just see an example of the kind of question that we're talking about with this. It involves trigonometric modelling, a bit of a classic Ferris wheel scenario here. So now let's just look at some teaching strategies around trigonometric models. How can we teach for a greater depth of understanding here? One of the really nice ways to do this is to start off this general topic with a recap of that prior learning around transformations, and use of graphing software obviously is really effective here. So plotting lots of different transformed functions, getting students to predict what they're going to look like, and following that up with questions like, give me the maximum or minimum point of the transformed graph, where is the center line now, so for example y equals 4. Can you predict for me what the graph of a given function would look like? So what about y equals 6 cos of x minus 20 minus 3? And keep asking the class and adding to that description and refining it until you've got a really full description. Where is that graph centered? So for example, y equals minus 3. What are the coordinates of some of the maxima and minima? And we can confirm that then by plotting in the graphing software. Again, we can start to develop a deeper understanding, saying things like, give me an equation of a graph with a maximum point at 30, 18. Is that the only one? Could you come up with any others? So really questioning very deeply around this to really strengthen that understanding of the connections there between the transformations that are happening, the functions, and whether actually, there are some equivalent functions that would do the same thing and give the same graph. And again, once we've recapped that prior learning, now is actually quite a useful time to introduce the concept that a trigonometric function can be a model for a real life situation. We could ask students, which of these scenarios would a trigonometric model be appropriate for, and why or why not? So it's going to start to allow students to think about and draw out those key features of a trigonometric function, that periodicity, smooth, continuous, symmetrical. It's also going to start to introduce some familiarity of those common contexts that we do see used in exam questions and exercise questions, such as your Ferris wheel, your depth of water in a harbour, and asking them to think about which ones might not be appropriate can also have some useful recaps, links to prior learning. So students might recognise that, the population of bacteria in a petri dish, actually that would be much more appropriate to be an exponential model. And again, that allows you to start to discuss things like limitations of models with them as well. A way to kind of, again, kind of supercharge this activity is to say, right, well, I'm going to give you maybe some information now about this Ferris wheel. It starts at 1 meter above the ground, maximum height is 21 meters, and a full revolution takes 4 minutes. Could we figure out an equation of a trigonometric model that would represent that, and allow them then to start to use their prior learning of transformations, the trigonometric graphs, to start to explore that and see if they can come up with their own equation. And again, we can confirm that by plotting in the graphing software, or they could use that to explore that as well and refine their answers. So there's real value to looking at this before we dive into kind of doing any of the work on converting one form to another. So at this point, we've not even really looked at the a sine plus b cos theta forms yet. This is a point at which you could then start to introduce that concept of equivalency by plotting the two equivalent equations and showing them that it gives the same graph. It's exactly the same model. So then we can have a chat about, right, well, why is actually, so here the y equals 5 cos of x minus 36.9, why is that a lot more useful form for us than the other form of the 3 sine x plus 4 cos x? How does it help us? What can it tell us about the model? And so we're establishing really at the get-go why that form's so useful and actually how we're going to use it. Then we can move on to teaching the skill, the procedural skill of doing that conversion. But you've also got the opportunity to boost that learning now by getting students to kind of also, if they're working through an exercise of just straightforward convert this form to that form, but also they could do as an add-on, right, now for each one, describe the transformation, give the coordinates of the first maximum and minimum, and then check your answer by plotting both of those, the equivalent forms on the graphing software. You can also extend to ask them to give the other equivalent form too. So, for example, if they're asked for the r sine of x plus alpha form, can they also work out what the equivalent r cos x plus alpha form would be as well, and come up with a context that their model could describe. So again, getting them to think in terms of context here. So that would really kind of supercharges that learning and helps them to really understand those what is otherwise just an algebraic expressions in isolation in the terms of the context of a mathematical model. So the last little thing we're going to look at as well is just about how we can use this problem solving cycle and kind of model this at every opportunity to support students who are really struggling with what to do when they don't know what to do. And also alongside those strategies, obviously, we're just going to make sure that students have got that kind of relevant toolkit of skills in the back pocket of stuff that they can try. Can they draw a diagram? Can they sketch the graph? Could they use the calculator to help them with that? Are they referencing the formula sheet where they need to? All of that kind of standard stuff. Okay, so to look at this in practice, I've got an example question here from the June 2023 papers. And this was a question that you can see from the performance data on the top right hand side that students really struggled with. The performance really dropped off from our A-star students, dropped off quite significantly, A grade only getting 62% of the marks, and then that drops much more significantly for our grade B and C students as well. When we actually look at the processing that's involved in this question, it's actually really accessible. So I would argue that this is a really good example of where it was the problem solving element that was the barrier to students rather than the mathematical processing that they needed to do. And if we can equip students with some skills, some problem solving strategies to tackle this, then all of a sudden this question becomes a lot more accessible and an easier win for students. So now we're just going to look at how we might model this problem solving strategy on this particular question. And this is going to be particularly helpful for the students, maybe those working in kind of those mid-range grades of kind of B and C's, who might really just not have a clue how to get started on some of these trickier questions. It's going to give them that comfort blanket of, right, I got no idea what to do here, but I do know that there's this and this I can do for any question, these steps I can follow that should provide me with some insight, and from that I might be able to then start to figure out where to get started and where this question's going to go and make some progress with it. So obviously we need to identify the command, which is to find a complete equation. Looking at parts A and C, it's the same demand but just with the different models. So we are going to have to work out the values of those constants as part of that. So collecting and organising the information, going through line by line to pick out those really key bits and interpreting that into some mathematical statements such as when t equals 0, h equals 2. And looking at the equation forms given. So the key here again is think, how does this function behave? How can I use my knowledge, but also use that toolkit of skills that I've got in my back pocket to figure that out? So, identifying that the first one's a quadratic and the other one's a trigonometric model. Oh, right, well, that's great. I know what a cos graph looks like, and I know a bit about transformations. So now I can start to think about what this model actually looks like and where its maximum might occur, and start to make that connection that the maximum would be when the cos bit was equal to 1. So that thinking there, those ability to either sketch a function, to identify its behaviour, is really the key to success in this question, and we see that coming through kind of loud and clear in the examiner's report when we look at it. We're then going to obviously, need to do some processing here, and the process is really straightforward for this question. Kind of, once you've understood how these functions behave, it's really quite nice and easy to go, all right, well, obviously now a must be 60. I'm going to sub that in, rewrite my equation, and I know that h equals 2 when t equals 0, and I can sub that in to find the value of the other constant. Interpreting my results, I need to make sure I've met the demand of the question. It was to give a complete equation, and we do have to write that out in order to get the marks here. And that checking process, let's maybe, before we move on, just do a quick check, substitute some of that information back into the equation that we've written for our answer, and just double check that those conditions still hold. So if I sub in t equals 0, I definitely get h equals 2, for example. And we can even apply the same strategy when we're looking at something like Part D, where students are asked to give a reason why the alternative model would be more appropriate, and a lot really struggle to give a valid reason for this. But let's look at how we might do that. So identifying the command. So we need to give a reason why the alternative model, hang on, let's double check back to the question. Yes, that's the trigonometric one, why that's more appropriate. So I'm going to have to write a sentence here, but at the moment, I'm not sure why. So what can I do now to figure that out? So let's collect and organise the information. Given that the carriage moves for 2 minutes, so we're being given some relevant information here. Let's use it. So that 2 minutes means that t would be 120. So let's process that now. We can use that t equals 120 and substitute it into the original and the alternative models that we'd already worked out in parts A and C, and see what happens. So this is now going to give us some values that allow us to figure out probably why one is definitely more appropriate than the other. And when we do that calculation, we can see that the original model actually gives a negative value for h, whereas the alternative, the trigonometric model, gives h equals 2. So those values are going to help you explain now why that alternative model is more appropriate, and we just need to then construct that sentence in context. So on screen, you can just see a snip from the notes to the mark scheme about some of the phrases and the references that were acceptable here and what wasn't accepted. Nothing that was too vague. Any calculations, if they were referenced, they had to be correct. But anything that was talking about that multiple cycles, that cyclical nature of the trigonometric model was allowable here. So again, students having that deeper understanding of the nature of the function, how it behaves, allows them then to successfully answer questions like this, where we're talking about why one model might be more appropriate than the other. And the examiner's report really draws this out, just some key points there from their longer report. But, those students that were able to be successful with this had a really confident grasp of quadratic and trigonometric models, and they were able to use that knowledge of the key features of those graphs to help them successfully answer the question. And again, we can see that the correct answers in part D were generally from students who understood the cyclic nature of the trigonometric function, or the fact that that quadratic was eventually going to go into the negative. So students that are able to visualize and understand how functions behave are able to much more successfully problem solve with these types of questions. So I mentioned a little bit earlier some resources that can help you students in gaining more practice with these types of questions with modelling, and there are some specific exercises in the textbooks. Quite often these appear towards the end of a chapter, and I know what it's like trying to cram everything into your lesson time, so sometimes these might end up getting set as independent work. Maybe sometimes it's worth a rethink about dedicating some lesson time to these, and maybe allowing students to work more independently on just practicing the process skills, but giving your time to them in that much more complex demand of applying all of those skills in the mathematical modelling context. So they are available, and they give some really valuable practice. And alongside that, we've got our PowerPoint resource of pure maths modelling questions by content area. This is also in addition to the kind of PDF resource of, I think it's about 93 modelling questions we've got from the old spec and new as well. This one's a bit more up to date, the PowerPoint. It's got some from the more recent exam series, and it's actually organised by content area. So you can see the snippet on screen here. It gives you all of the past paper questions that involved a trigonometric model. And you've got links there to the original question, the mark scheme, and the examiner's reports. So a really valuable resource to make sure that you've got ready access to those modelling questions to practice them for each topic that you are teaching. So thanks for taking the time to watch this video today. I'm your subject advisor, Vicky Wood, and if you do have any questions about kind of the course, delivery, marking points of principle that you'd like to ask myself or the examiners, then you can email us at teachingmaths@pearson.com.